Today, Alon will talk about character rigidity for non-uniform lattices. Alon, the floor is yours.
Okay, thank you. I'm honored to be here, and thank you, Michael, for making this happen. Right, so today I want to talk about, I'm giving a broad talk, like I'm not assuming you have background either on high-rank lattices or on character rigidity. I'll try to make it general, so please ask questions that you're not bad at that. Yeah, but the work, I should say, is joint work with a few students at Weizmann Institute. So Michael Glasner, Yuval Gorfein, Liam Hanani, and Aryeh Levit, who's a professor at Tel Aviv University. But I kind of, so let me start by giving the background and motivation. So a lot of the work, most of the work is going to talk about like a beautiful family of groups called higher rank lattices, but because we're not necessarily all comfortable with it, I want to give you like the single most important example for me, which is the following group. It is SO2D, but not just integral matrices. I allow dyadic integers. Right. So what is this? This is just matrices A, B, C, D, where A, B, C, D are in this ring, and the determinant is 1. Okay, so this is the most important example, and if you follow the talk with just thinking of this group, it's good enough. Okay, but some other groups which are also important to consider is so here are examples, right? The second example is SL3, but this time just integral matrices, not with dyadic integers. Right, it's just 3 by 3 integral matrices with determinant 1. And maybe a slightly more sophisticated example is what I would write as SO. Sorry, N1. Any questions?
Start one with property P.
No, that's the point. I will give you a differentiation. The top one is more similar to that last one, which I will. This is a good remark, and it's the reason for this talk. Okay. All right, but let me just give you. So the last one will be a generalization of this one. What is this group? This is the group of matrices in SLN plus 1 with entries in the dyadic integers. All right, but with an extra.
Can you write here?
Yes, I will. Let me. Yeah, I understand. Legitimate. Let me write what is this group here. So the first, so this is 1, this is 2, and this is 3. The third example is the following matrix group. It's n plus 1 dimensional matrices with dyadic integer entries. But now I require that preserve the Lorentzian form. This is the correct spelling. Right, this is just the quadratic form x1 squared plus x2 squared plus xn squared minus xn plus 1 squared. So so this is the group of this is a transformation group. It's a classical group of the space-time, right? And they preserve this is if I wrote here R. And in a second, I will address the Lie groups here. This would just be the isometry group, the orientation preserving isometries of the hyperbolic n space. Okay, this is, but this is like explicit matricial description. And more importantly, these are all examples of so-called arithmetic groups. Arithmetic in the sense that instead of talking about real matrices here, I'm assuming that the entries come from some arithmetic rings, right? And by the way, you can replace half here with square root 2. This would also be a relevant example, right? So there are like various different examples, but an important remark which Alon pointed out is that, so the second example, SL3Z, has what we call property T, which I can remind if anyone needs later, please ask. But so this is kind of the somewhat easier example for what I'm going to talk about today. And but 2 and 3, well, 1 and 3, these don't have property T. T. But, and this is kind of part of the motivation for the talk, they have what's called property tau, meaning if you look at all Katie graphs obtained from finite quotients of this group, choose any finite index subgroup of this group, take the quotient, the graphs would be an expanding family. Okay, all finite quotients. Okay, so this is kind of, think of this example only. If you're a bit more comfortable, if you're comfortable with hyperbolic n-space geometry, think of this example. And these would be like, this is enough to think about. And I will write, but okay, so the main thing I want to kind of, the origin of a lot of the works I'm going to talk about is the celebrated Margulis normal subgroup theorem. And the nature of Margulis's work and its power is in its generality of capturing more than just specific examples, right? It's kind of at the same time capturing in particular, most of these arithmetic kind of groups, but there is the key condition is called higher rank. So these are arithmetic groups, and let me before stating Margulis, let me just say a theorem of Borel, Armand Borel, and Harichandra. Borel. Harichandra is for a single person, is that all examples like this are lattices in respective B groups. And let me make it explicit, right? One, for the first example, okay, it naturally sits inside SL2R, right? These are real matrices. But to make it a lattice, that's not the correct Lie group to consider. You need to consider gamma inside a product of 2 copies of SL2R. What is the reason? This ring, Z half, is dense inside the real integers. It doesn't consist of the discrete subgroup.
The real number.
The real, yeah. This inside R is dense. But inside, under the diagonal embedding, it, sorry, here it shouldn't be SO2R, it should be the p-adic, 2-adic integers, because I did half. If I did square root 2, then it would be a product of 2 SO2Rs. But for us, there is a difference between these two, but for us, both, let's think of Z half in this example. Right, so it's not a lattice in a Lie group per se, it's a lattice in like a Lie group, but also like p-adic analytic groups. But the point is, you should take that I have a product of at least two factors here. What I'm going to say is definitely not true for SO2Z, which is essentially a free group. That is a lattice in SO2R. But the higher rank condition is the fact that I have at least two copies of SO2 type groups here. Right? So this is this by lattice we mean finite, discrete, and importantly finite covolume. Meaning the quotient manifold is a finite volume locally symmetric space. And of course, 2 is a lattice in SO3R, because here I just took integers and not half. But the fact that I have 3 here instead of 2 will make Margulis's result true as well. And thirdly, gamma is inside SON1R, right? So this is isometries, basically isometries of the hyperbolic n space. But here I also have a p-adic factor, right? The same, for the same reasons. Okay, and I should say that these are all what's called higher rank. I don't want to get too much into what it means exactly, but for us here, for SLN, I just mean n is greater than 3. And for SO2s, I just mean, or SON1s, I mean that there's at least 2 factors. Okay.
That's the definition of higher rank.
Yeah, so the rank of a semi-simple Lie group is the sum of the ranks of the simple Lie groups, and you can compute it for each, like we have a classification and we know what it is. It is the dimension of a maximal totally geodesic subspace, which is Euclidean. Right, so in hyperbolic n space, you only have geodesics and nothing different. I mean, it has a geometric meaning. All right. But let me quote Margulis now. This is the main theorem. And put the adjectives, but really you should think of this. So let gamma inside G be a lattice, an irreducible lattice. So I should add the adjective irreducible, and that just means essentially that I'm not taking a product of a lattice here and a lattice here, right? It has dense projections, as we mentioned. So
every lattice is irreducible.
Sorry?
In SO3R, every lattice is irreducible.
I mean, irreducible only says something when you have
Okay.
at least 2 factors. It just means dense projections on the factors. Okay. Well, in one factor, of course, you don't want the dense projection. Yeah. So if I have an irreducible lattice in a semi-simple Lie group, I mean, technically, as we said, we have p-adic Lie groups here, but Margulis's theorem is true there as well. But just let me use it, the collective term semi-simple Lie group. Yeah, so I have a higher rank, an irreducible lattice in a semi-simple Lie group G with higher rank, and by that I just mean that the rank of G is at least 2. And I gave you meaning here.
You gave examples.
I give examples, yeah. And finite center, although this is not really important. Then we have the following amazing corollary. Every normal subgroup n inside gamma is either central and the center of gamma is the same as the center of G. I mean, in these cases, we're mostly center free anyways, or it's like the center is an ordered 2 group, something like that. So essentially, I could have talked about like center free Lie groups and said either the normal subgroup is trivial or of finite index. And this theorem kind of says that the Lie groups, right? We kind of know from classical theory that they're semi-simple or simple Lie groups. They don't have closed. We know to exactly what are the closed normal subgroups of such a product. It's just partial products or the center. And Margulis's theorem says that up to having finite index subgroups, which you cannot avoid, the same thing is true for the lattices, for the discrete groups inside these continuous objects, right? And I should say that for these specific examples, showing this theorem, I mean, this theorem was known before Margulis. The real power in this theorem is to be able to deal with any such discrete group, just by the fact that it has a finite covolume and is a discrete subgroup of a semisimple Lie group, right? And
So some
Yes.
condition about compact factors.
sorry?
There's a condition about compact factors. Or
No, I don't need a condition. It can be co-compact.
no, the group G doesn't have the compact.
It doesn't have real, yeah, it's a semi-simple Lie groups without compact factors or like Euclidean factors, you mean, right? Like Rn.
And there are SN.
What's the problem if I have an SU2?
And the normal group can just be.
But if you project to you can project it to the non-compact factors and it's okay, right? I mean,
No, I just remember that it had the condition that I can, maybe I misremember it.
okay, I think it is okay, but there are several adjectives and maybe, but yeah, I mean, by semi-simple Lie group, I mean, yeah, as we said, we interpreted it here, but you actually to construct co-compact lattices, right? These lattices are of finite covolume, but the quotient won't be compact. And there exist lattices for which the quotient is compact. For example, here, where the quotient is a closed hyperbolic manifold. But to construct them, you actually need compact factors sometimes. So the theorem is true for them as well, and that's actually the novelty in Margulis's approach. The fact that you can deal not just with these examples, but more sophisticated examples where the group is co-compact. Yeah, but this is intricacies that I don't really want to get into today. And okay. But what is the proof idea? And this is ingenious. Margulis showed that that if M is a normal subgroup, which is not contained in the center, then he showed 2 theorems, which are, I mean, one theorem is actually due to Kashdan in many cases, but first of all, gamma mod n has property T, meaning its unitary representations have a uniform spectral gap. And this was known, this is easy if G has property T, right? But Margulis managed to show it regardless of whether G or gamma has property T. He showed that if n is a non-trivial normal subgroup, then always the quotient has property T. Secondly, he showed that the quotient is amenable. So it's funny, like you have these 2 defining properties of analytic group theory. On the one hand, having a spectral gap for all unitary representations. On the other hand, the regular representation does not have a spectral gap. And the conclusion is that the quotient is finite. And this is like a proof that you wouldn't expect to work, but it works. And actually, more than the fact that it works, it's good to generalize to other settings. And this is what I want to talk about next. Any other questions about Margulis' theorem? All right, let me now talk about the Stuck-Zimmer theorem and invariant random subgroups. So this is a work that kind of took Margulis' theorem and tried to ask, can we get like in some way a probabilistic version of it? Let me first state it in like an ergodic theoretic manner, but then state it in like a more probabilistic manner. Right, so here's the theorem. And I think it's right to add the name of Neveu because there was a mistake in the original works of Stuck-Zimmer and it was only corrected after extra work of Neveu. So the Neveu-Stuck-Zimmer theorem. Same setting. And importantly, they assume gamma has property T, which is the same as assuming G has property T. Then every ergodic probability measure preserving PMP action, this just means I have some probability space x mu and gamma acts by measure preserving automorphisms. And let me here assume that that the center is trivial. I mean, otherwise you can adapt the statement. Is either the action is essentially free, by that I mean that the measure of fixed points of non-trivial elements is 0. Or the action is essentially transitive and a finite orbit. What do I mean by the last condition? I mean that up to measure 0, in fact, X is an atomic space, which is just like a quotient by a finite index subgroup of gamma. Okay, so the moral of the story is unless you have some degenerate behavior, like as soon as this space is non-atomic and ergodic, then and the action is like rich enough, then this action is automatically free. Okay. How can we relate it to this above theorem? The key connection is to look at the stabilizers of such an ergodic action, right? So, like equivalently, I can say it as follows: any IRS. So let me write it out: invariant random subgroup, and I'll explain what I mean. H distributed, I don't know, according to some law. Right. So what is an invariant random subgroup? By this, I mean a random variable with values in sub gamma, the set of subgroups of gamma. right? So I just mean a map from a probability space to the space of subgroups on gamma, a sampling scheme for a random subgroup, with the extra condition such that the distribution is conjugation invariant. So it's not just a random subgroup, it's kind of a random normal subgroup. Meaning if I take this random variable and conjugate it by some group element, then this distribution doesn't change. This is a Michael Chapman way of defining invariant random subgroups, but I mean, this is not the original way it was defined, but it is what it is. Right, so I'm talking about like someone gives you a machine to sample a random subgroup with the guarantee that the distribution doesn't change under group conjugation. Then the conclusion is either so H is of finite index with probability 1. I should add here ergodic.
So you're taking a measure on sub gamma.
Yes.
It's invariant on the conjugation.
Yes, and an ergodic one. Yeah, but this is like just a slightly different. Yeah, so the distribution is invariant, exactly. But it's a measure on this space, which is a compact gamma space with conjugation, which is invariant and ergodic.
Yeah, and ergodic means that it's not a convex combination.
Yeah, exactly. The law is decomposable. Then either with probability 1, the subgroups you sample are of finite index, and when it's ergodic, it's just the one finite index subgroup and its conjugates, or H is trivial with probability 1, or central, whatever you. Right, so you have this kind of strong dichotomy that can be considered as a probabilistic version of Margulis' statement.
And it can't be finite because you're assuming the center is finite.
Sorry?
It can't be finite because you're assuming the center is finite.
Yeah, it will be finite if I'm assuming the center is finite.
Yeah.
I should say, by the way, for people who do like Lie groups, that in fact Margulis' theorem and Stuck-Zimmer theorem, and the theorem I will say, is true for Lie groups with infinite center. Right? So there are examples of Lie groups with infinite center, the same statements hold. All right. Now for the fun part, which is character rigidity. I mean, it's all fun, but that's the most fun for me. Any further questions about this second level of generalization?
No.
Now we're going to do the final
Can you
one.
just explain why essentially free is what is a trivial group?
Yeah, because what does essentially free mean? Okay, what is the invariant random subgroup associated with a PMP action? Just a random stabilizer of the action. If you take a PMP action, by the fact that it's measure preserving, if you sample a random stabilizer in this action, it will be conjugation invariant. And saying that the random stabilizer is trivial exactly means that the action is essentially free. Yeah. Right, but now for something a priori completely different, we're going to do some representation theory. Right, so let me define the object. A trace phi on a group gamma is a function, a positive definite function phi from gamma to C. So it's scalar valued such that the following three conditions hold. First of all, it's normalized. Two conditions hold. And positive definite I can find, but it really means that it comes from a matrix coefficient of a unitary representation. And secondly, and the important condition, which is what differentiates it from just usual representation theory, is the fact that it's also conjugation invariant. Okay. And this was defined by Elmar Thoma, I think around the 30s, I'm not sure. And why is this object interesting? Thoma not just defined it, I mean, definition is easy enough, but he proved that these objects capture a certain part of the representation theory of arbitrary discrete groups in a way that you can hope to classify. So, I mean, people realized already in the beginning of the 20th century that for most discrete groups, you cannot hope to classify all unitary representations. But this trace thing, which is analogous to a character of a finite group, directly generalizing it, captures a certain part of the representation theory, which you can hope to classify. And so let me state it as a theorem. So,
Sorry, so.
yes.
What's the definition of
Positive definite, let me capture the definition inside the theorem. Okay. So the following are equivalent. First of all, phi is a trace on gamma. I denote by trace gamma the set of all traces on gamma. Secondly, there exists two unitary representation, pi and rho, from gamma to some Hilbert space, and commute such that they commuting unitary representations, a unit vector psi in H, which is invariant under the diagonal action pi g times rho g psi equals psi. And this is the definition of a positive definite function. Phi is the matrix coefficient of, say, pi. You can actually require it also the matrix coefficient of rho. Without the third condition, a normalized positive definite function is just, you give me a single unitary representation on a prior infinite dimensional Hilbert space, and phi is given as the matrix coefficient. For it to be a trace, I need two unitary representations and for them to commute and preserve the vector diagonal. Meaning pi g and rho g commute for every g. Sorry, pi g and rho h should commute. So pi g rho h is always one or zero, i.e. 0. Okay.
Can you just, if I take the free group of two elements, I take the usual trace.
Yes.
away, then what is this? What is
It will be
phi?
so pi will be the left regular representation, rho will be the right.
Yes.
Yeah. So that's the reason why the regular representation of a group is always like, it has an extra nice property that you can, part of why it's special. And let me say the third one, which, most audience won't be able to understand, but if you do understand it, it clears. I mean, this is already.
The regular representation is special because you have the right and the left.
Yes, I'm saying the fact that you have both the right and left regular representation, and the fact that the cyclic vector at the identity is like if you take pi g delta e rho g inverse, right? Then it cancels out. So this makes it a tracial representation. Okay, and
This proves that trace of gamma is always nothing.
yes, or the trivial representation. Yes, that's true. And this will be what we want to talk about. But I'll give you more examples. But let me just say for Piscinas that this is the same thing as a unitary representation into n where M tau is a tracial von Neumann algebra. For people who know what that means, and phi is just given as taking the trace of the representation. So really, this definition, like if you know what it means for tracial von Neumann algebras are kind of infinite dimensional generalizations of matrix algebras. And the fact that you can represent into them, you can also take, they come with a trace, in the same way that you trace out a representation to get a character on a finite group, you can trace out a tracial representation to get a trace or a character. Yeah. And this correspondence is kind of one-to-one. The fact that two representations have the same trace gives a natural form of, it's called quasi-equivalence of the representation. And what differentiates it from usual representation theory is the following fact, I mean, easy to see, is observation that this trace space of gamma is a compact convex set. Right? I take two traces on the group. I can take convex combinations. And also I have the topology of pointwise convergence. Right? This is a nice topological space that I can hope to identify. Right? And I have two questions. One is, given gamma, can we describe the extremal traces, right? Because just as in representation theory, instead of you can describe irreducible representations, I should say this is a Choquet simplex. This is a non-trivial fact, but what this means is that each point here is represented by a unique measure on the extremal points of this compact convex set. So can we describe the extremal points of this thing, which by definition is what I call the characters of gamma? And usual characters of gamma, like homomorphisms to C, there would be such examples, so you know. And the second question is how well approximated the character space of gamma is by finite dimensional characters. And as I alluded to, if you take a finite dimensional unitary representation and take its normalized trace, it gives an example of such a tracial representation. You can think of as an exercise how to see it using the second definition. But this is kind of a general question I can ask, right? I associated some a priori infinite dimensional compact convex set, which is a Choquet simplex, with my group. And I'm asking, like, can you identify it? So let me give you some answers.
For finite dimensional characters?
Right, Alon, we need to
Yes.
suggest what happens.
Finite dimensional characters or just?
Yeah, so
Characters of finite.
so phi
One.
equals 1 over d, the trace of pi g, where pi is the finite dimensional unitary representation. This is called finite dimension. Finite dimensional trace. And if this is an irreducible representation, this is called a finite dimensional character.
What does approximate mean?
So, I mean, this is a compact convex space. It has a topology. Pointwise convergence. Yes, that's important.
Can get it.
Sorry?
Not every linear combination of
Convex combinations.
convex combination is a
But it's a trace. No, the space of traces
Yeah,
is
So
a
the
convex
extreme
set.
points, right?
Yeah, just
The characters are
extreme
extreme.
points are the irreducible ones, and
Yes, exactly.
you also get some rational combinations, but not.
The extremal ones are not,
Yeah.
extremal ones are not rational combinations.
Yeah, okay, no.
Yeah, no, these ones, if you're finite dimensional and not an ERIP, they are exactly rational combinations.
Yes.
Okay. So the second question, right, which is here, is this set, it can be uncountable, right, depending on how many finite dimensional representations you have. Is this dense in this topological space? Right, or at least the characters. It's actually the same thing as being dense in the extremal points and all of the traces, because you can take complex combinations. But anyway, you get the idea. So let me give you some answers. Let's start with the both best and worst example, the free group, right? So the trace space of a free group is a Poulsen simplex. This is a theorem of Horowitz, Ras-Lutzky, and Itamar Viktorovich. Poulsen, Poulsen is a name, I'm not sure who it is, but the Poulsen simplex, by definition, is a Choquet simplex whose extremal points are dense, which is very counterintuitive. It's very infinite dimensional, so much so that you have so many extreme points that you don't need to take convex combinations for it to be dense in all traces. In particular, this means that the character space of F2 is homeomorphic to a Hilbert space. Like, it's very continuous. Okay. That's on the one hand.
Wait, is it F2 or FN?
FN. Yes. On the other hand, the Poulsen simplex is an ubiquitous and canonical object. There's only one Poulsen simplex. It's the unique one whose extremal points are dense. And for all n, it's the same thing. So treat this result as you want. I mean, the same thing, by the way, is true about IRSs of the free group, and this was proven by Bowen. This is, I guess, some answer for question one. I would still like a better answer to say that you cannot give formulas for the characters of the free group, but I'm not sure how to do that yet.
What did Bowen prove?
Bowen proved that the set of IRSs of a free group is a Poulsen simplex. And this was this.
Think of IRSs in this context.
Sorry?
How should we think of IRSs in?
IRSs, the set of measures.
Yeah, no, but
No, it just the translation is given an IRS. For every element, you can ask what is the probability that the sampled subgroup contains this specific element. This is a function from the group to the numbers between 0 and 1. That's the probability that the specific number appears. Turns out this is a trace. It's always a trace. The IRSs live inside the hard cells. They can have the same, you can induce the same topology, and you can ask
and you can recover the IRS from this.
No, these are different results. I will talk about this.
No, but you can recover.
What do you mean?
Said an IRS is a trace, and this is an embedding.
Okay, maybe let's talk about it later, because I don't have too much time. The second question is even more interesting. It turns out that not every trace of the free group is a pointwise limit of finite dimensional traces. And this is a result, this is equivalent to the negative resolution of Kahn's embedding conjecture, and as such proven by the MIP star with R. But this is highly non-trivial. Until this result, we did not know of a single example. We did not know of a single example of a group which has infinite characters which are not well approximated by finite dimensional means. Okay. Yeah, and you know who are the co-authors for this. I can mention it later.
Do you have a meaningful characterization of which characters can be approximated by finite dimensional?
These are called hyperlinear characters, and these are exactly traces which generate Kohn-embeddable algebra. Like I had this thing, right? So it's exactly the same thing, a character of the free group is approximable exactly when it generates a combinable algebra.
Kind of hard to tell, but I'll give you one.
Yeah, I mean, probably undecidable. Yes,
I see.
yes. I mean, you probably can prove it, but I don't know. I mean, what does it mean to give you a character? There are many complexity theoretic questions you can ask here. Like, for example, this I don't see still as an anti-classification result. Like, what does it mean that you cannot give formulas for characters of free groups? Okay, but let me go back to Margulis, right? And so, this is kind of, the same results are true, I think, for SO2Z, right? Back to arithmetic groups, right? And there's a conjecture that Kohn made as a result of Margulis's work. So just to tie off the knot is that any higher rank lattice is character rigid, and I'll explain what that means. Each character of gamma is either finite dimensional or the character of the regular phi of g equals 0 for every g, let's say non-central. If the center is free, I just mean that the character is the Dirac mass at the identity. And okay, I should mention that okay, so what are the open problems at this point? This is a different, I mean, one was the Kohn-embedding conjecture, but this is a different conjecture of Kohn. Which is, yeah, unlike the Kohn-embedding conjecture, it's more true. I mean, we still don't have a full answer for this, and I'll explain what we know. Right, so another conjecture I want to say, called the Stuck-Zimmer conjecture. But really, I think the one who stated it first is Gelander, is that the conclusion of invariant random subgroup rigidity, or Stuck-Zimmer's theorem, holds regardless of property T. Right? I emphasize that the Stuck-Zimmer theorem was only known for the case where the group has property T, or at least one factor has property T. So this is open in general for lattices in SO2R times SO2R, for example. Okay, and by previous works of relatively recent works of Boutanet, Houdayer, Johanna, and Peterson, this conjecture was resolved in the same way that Stuck-Zimmer, in the same setting of Stuck-Zimmer. So as long as G has property T or gamma has property T, then Kohn's rigidity conjecture is true. Actually, Kohn rigidity is another conjecture, so I'll just say it's Kohn's conjecture. So let me write that actually. So Boutanet, not Johanna, Boutanet, Bader, Henri Bader, Rémi Boutanet, Cyril Houdayer. I mean, there were multiple works, but this one contains all relevant co-authors, Peterson. So it's true if gamma is in a lattice in a Lie group, and G has a property T factor. So like SO2 times SO3 is also fine. But up to recently, I mean, there was only a standout work of Peterson and Tom. Which shows that specifically groups of the first form I talked about, SO2Z half, for example, is character rigid. Right. So even though this group does not have like an extremely strong spectral gap property, Margulis's philosophy, not Margulis's philosophy, because this proof is different from Margulis's proof for the normal subgroup theorem. It's more similar to what one would call the congruent subgroup property proof. But even though this group does not have property T, so you cannot just blindly apply the property T part of Margulis's proof, you can still deduce character rigidity. And more importantly, Peters and Tom also showed that that Kahn's conjecture, so character rigidity implies IRS rigidity. It's not exactly clear, right? It's not too hard, and I can say it afterwards if I have time, to, out of an invariant random subgroup, obtain a character. It's just the function which gives back the measure of fixed points in the action, or the probability that a random subgroup contains a specific element. This turns out to be a trace. And from Kahn's rigidity conclusion, you can actually show this theorem. All right, so let me almost end after this long introduction with our theorem. Glasnow, Gofine, so T, Anani, Levitt. Yeah. So this is kind of the best known form of Kahn's rigidity conjecture. So if gamma is a higher rank lattice, such that G has a T factor, so by previous works this was done, or this is the new part, gamma is not co-compact, meaning G mod gamma is not compact. So any of the examples I gave you at the beginning. Then gamma is character rigid. So out of like the three examples I gave you at the beginning, like the new part is for say higher dimensional hyperbolic spaces, and even like complex hyperbolic spaces. But
I mentioned tau before.
yes,
Tau is automatic in these cases. Or...
tau follows. No, it should be clear. Tau doesn't follow as is from what I said about character rigidity, right? It's actually, is it used? Tau is not directly related to this statement. This statement is a Kahn's statement is a classification result for some infinite dimensional representations, and tau is a spectral gap property for finite dimensional ones. As a result of Kahn's theorem, and in fact, as a result of this theorem or Kahn's conjecture, and in fact it is equivalent to it, you can say that this theorem is a spectral gap theorem. We show that every tracial representation of the group still has spectral gap, right? They are already a priori infinite dimensional, and by the end of the day, they're just a regular representation or finite dimensional. So together with property tau, this theorem says that the tracial representations of the group have a uniform spectral gap.
But wait, like,
Yes.
I didn't answer the Ron's question, right? Like,
What was the question again? Sorry.
Not sure, but you know, you mentioned tau before. I thought it was one of the assumptions
It's-
you made, but here it's.
No. First, okay, tau is known in these cases, right? As long as you have a property T factor. Okay, maybe I should back up. There's Lubotsky's property tau conjecture, which is the same thing, saying that all high rank lattices should have property tau. By now, this theorem is known more or less in, so I'm not sure, but more or less in the same generality. The issue is again, when you don't have a property T factor or that your group is not compact.
Sorry.
Right, so the same difficulties arise. And the thing we really use here is the congruent subgroup property, which is another important property. But again, you have like these several things which are problematic when you don't have enough spectral gap or your lattice is co-compact, which is the difficult case. But I mean, okay, up to this theorem, the cutting edge was really dealing only in full generality when you have a property T factor by this series of beautiful works. And these works proved character rigidity using Margulis's philosophy. They realized how to take amenable and take property T and generalize it to von Neumann algebras and prove it that way. The proof for non-uniform lattices in product of rank 1 groups, as well as Peterson and Thom's theorem, which was for these specific class of arithmetic groups, they're more algebraic in nature, right? So the ingredients in the proof is first to use Margulis's arithmeticity theorem, right? After these works, we're basically dealing with non-uniform lattices in products of rank 1 groups. So we can apply Margulis's theorem, which says that in fact, all these lattices come from some arithmetic type. They come from an algebraic group and really are not too far away from the examples I gave you at the beginning. Take some algebraic group and plug in a numbering. Okay, that's the first step. So we have some understanding, and by arithmeticity, we see that gamma is more or less a group of the form G. Some algebraic group with values in the number ring, but such that gamma has an R here. Think of, okay, I can say many words, but let me just say Z half, okay, or this is good enough. This is like when you're in SO2R times SO2 QE. And the really important thing that we use is that gamma has an infinite order diagonal matrix, say, meaning in the torus. Let's go back to this SO2 example, right? SO2Z half, unlike SO2Z, and this is really the crucial difference between why this has a bunch of rigidity properties versus SO2Z, is the fact that you have diagonal matrices of the form A inverse, where A is a unit of this ring. Right? The ring Z has only 1 and -1 as units, right? Unlike the Lie group, the arithmetic group doesn't have really any diagonal matrices, right? Because you want two integers who multiply to 1. You can't do that. And you want A to be a unit, for this to have determinant 1. Right? And only when you have a non-trivial localization or a number ring with infinitely many units, can you have such a thing in the torus. And the next steps kind of use this diagonal subgroup and its dynamics on upper triangular matrices. So this thing acting on upper triangular matrices, the idea is to assume your character is not finite dimensional, right? And then slowly by some, I would say Halmor or dynamical arguments show that it vanishes on more and more of the group until you only reach the center, right? But to apply dynamical tools, you need a non-trivial kind of thing to act on. You have this semi-simple diagonal element acting by conjugation on the additive group, and somehow you can first of all classify characters of this semi-direct product and slowly build up vanishing results by algebraic elements. I'm forgetting about Margulis's philosophy and just using explicitly nilpotents and like semi-simple elements and playing with them together with some von Neumann algebraic input. But yeah, I think at this point it's better for me to pause, and if you have any questions, I can answer them about more specific parts of the proof. But of course, now by this time, similarly to many other influential conjectures in lattices and higher rank Lie groups, the difficult part is to talk about co-compact lattices in products of rank 1 groups. So give you a lattice in SL2R times SL2R, which is co-compact, meaning the same as giving you like a locally symmetric space, a quotient of this guy, which is compact. What can you say about the characters or the IRSs of this group? We don't. So this is a very interesting question, and this is the Holy Grail, but this is what we know for now.
Question?
Yeah.
Does your strategy works on SL3 of Z?
So
Because I don't.
No.
That makes you see.
yeah, so SL3 of Z, this was actually the first result, and I should have said it. This was done by Becker, Bashir Becker. And our method is both similar to this method and different, right? Because the essential difference is, okay, of course here you don't have these diagonal elements from the usual diagonal, which have integer entries, right? You need another source of richness in the group to play with dynamics. And here you use the fact that you have like many unipotents, whereas here we only had like these upper triangular unipotents. And so the proofs are different in like their algebraic nature, but the idea is similar. We use many of the ideas that came into Becker, like this idea of showing vanishing more and more on the group, but it's implemented in a completely different way. I would like in a different way. And the intricacies here are different from, some intricacies here are different from the intricacies here, but there are many common elements like the congruent subgroup property.
I have a terminology question. In
Yes.
those items, it was you were speaking about
Non-uniform
lattice.
No, non-uniform lattice.
And non-uniform lattice means that the lattice is not.
It's not co-compact. Yes, sorry, I should have not mixed the terminology.
No, that's
Uniform is the same as co-compact, so I'm talking here about non-co-compact lattice.
Okay. So, I mean, probably the answer is trivial, but you haven't said anything about your second question here. Is it obvious? So in this Cambridge situation, you only have a regular representation. Could
Yes,
always be
and it is approximated. Yes, so Kahn's question answers both questions positively, right? So this is another difference from, I mean, before, okay, it's kind of an extremely strong way to resolve the second question, right? I'm saying only the,
Is it obvious? that
yes,
the regular representation
so gamma is residually finite if and only if implies that the regular representation, is like approximated. Pointwise. Yeah. In fact, the fact that this character is approximated pointwise is the same as saying gamma is a hyperlinear group. This is because this is the same thing as saying that the group von Neumann algebra of gamma is Kohn-embeddable. Sorry.
That's mysterious for most people, so like.
No,
The fact is clear. Okay.
the first, okay, so, but, no, I'm saying in the same way that the group is sophic, if and only if its Cayley graph is approximated by by some kind of finite actions, this is said to be hyperlinear or equivalently hyperlinear if the regular representation is approximated by finite dimensional.
That's the definition.
That's the definition, yeah, but then-
Groups usually.
Yeah, but no, sorry, there is a mistake. This is not the same. This is not the same as saying that this group is hyperlinear. Saying that this is in fact equivalent. Sorry, so I should be a bit more careful. Gamma is residually finite if and only if the Dirac, assume it's finitely generated, okay? If and only if the Dirac trace is a pointwise limit of finite dimensional representations of gamma. That's it. Okay. When you allow approximate representations of gamma, this is the same as hyperlinear, but that's a different thing.
Let's thank Alon again.